Jnanam Paramam Dheyam. Knowledge is supreme.
All right. Now we after the digression on the signature of a permutation, etc. Now we come to the proof of the lemma as stated. So the lemma we wanted to prove was, so this was the lemma, that for every permutation sigma in Sn, if I permute the Vandermonde determinant variables, that is, if I write V of sigma 1, x sigma 1, etc., x sigma n, what I get is sine of sigma times the Vandermonde determinant. So this Vandermonde determinant is not invariant under all permutations, but it is invariant under only at the permutations whose sign is 1. That is the advantage. So proof. So what was the Vandermonde determinant was by definition was this V x1 to xn. This is the product. Product is running over these indices I less than j, xj minus xi, and I wanted to apply sign. I wanted to apply sigma to these variables. I want to permute the variables according to the sigma, and so the proof I am going to give, this is a proof due to Jacobi. That was in 1841, because Jacobi studied what happens to the Vandermonde when you permute the transpositions. When you apply a transposition to the variables, what happens to the Vandermonde determinant? Jacobi studying that. So that means, so it is enough to prove, it is enough to prove that, to prove this formula for transpositions, because every, we saw in digression that every permutation is a product of disjoint cycles and every cycle is a product of transpositions. I am not saying disjoint transposition, but transposition. So altogether every permutation is a product of transposition. So and the sign is a homomorphism. So sign commutes with the, whether I compose the transpositions, apply the sign, or take the signatures and multiply that. So therefore it is enough to prove for sigma equal to tau, where tau is a transposition. Because remember, if sigma is a product of R transpositions, sigma tau 1 to tau r, these are tau is are transpositions, then sine of sigma will be minus 1 power r, because here I am using sine is a group homomorphism, and sine of a transposition is minus 1. This, therefore, enough to prove that I have to prove this V of x1 to xn, and if I apply tau to this, I get minus of V of x1 to xn. This is what we have to prove. This is enough to prove. All right. Note that by definition of this Vandermonde, I will rearrange this product, and when I rearrange, I will have to multiply by plus minus 1. So note that there exists epsilon belonging to plus minus 1 such that this epsilon times xj minus xi. Okay, and now I am assuming I want to prove this formula for tau. So tau is the transposition ij with I strictly less than j, and then I want to prove this equality. So find epsilon which is plus, which belong to plus minus 1, this times product is running over k is in between 1 and n, and k is not in the set ij. This is xi minus xk times xj minus xk, and still I have to no place here but the product. Now this product is running over L and M in between 1 and n, and L, M both are not in ij, and this product is xl minus xm. So here I should have written m is strictly less than L, m and L in between but it is strictly less than this, and L and M not in I and J. So I have rearranged this product. See, originally this was a product x. Now I will write xl minus xm, 1 less equal to L less equal to M less than L less equal to N. This was the definition, because I and J are fixed here, so I do not want to use that running index. And this I want to rearrange this. First of all, if L and M they are different, they are not in I and J, because none of them is I and J, then I have kept that as it is. The remaining factors will have the property that L and M is ij, or they are different from. So that is this is, and then while rearranging this I might have had to apply by some either minus 1 or 1. So this is very easy. Now I have to apply tau to this. When I apply tau to this, what happens? So therefore tau of v of x1 to xn, this is what we want to compute. This is tau v of, so I am applying tau to this side. So that I push that tau inside, then what will happen to this? This epsilon remains as it is, and this I and j get changed. I and j, this becomes xi minus xj. And this factor does not change now, because this will go to this and this will go to this. So this factor does not change, because this will go to this and this will go to this. So the factor does not change and this one do not change at all. Therefore only one change happens, namely this change. This has become this. So therefore it is obvious that this is equal to, so remaining is as same as it is earlier, and therefore this sign h, this epsilon also remains same. So therefore the tau of this v is nothing but minus v of x1 to xm, which is equal to sine of tau times v of x1 to xm. So therefore we have proved our lemma that, so this proves the lemma. All right. Now remember our problem was to define discriminant of a polynomial. So I am going to define first. So we will first define discriminant DISC, discriminant of Fn. This is a general polynomial of degree n. So, I have this polynomial Fn equal to x minus x1 etc. x minus xn. This is a polynomial. The advantage here is I have the variables only, so I can play around with the polynomial. So, I want to define the discriminant of this. Alright. So, you take the van der mode of x1 to xn and take its square. So, what is this? Before taking the square, it is the product 1 less equal to I strictly less than j less equal to n and xj minus xi, and I take the square. So, I take the square inside. This is by definition discriminant of Fn. This is called a discriminant. Of Fn. Now, where is this? Note that this is clearly a polynomial in n variables over k. And also note that, see, I have taken the square. Therefore, it is very clear that for every sigma in Sn, sigma of dfn is, I will just abbreviate this by v. So, this is v square. This is sigma of v square, which is sigma v times sigma v, but this is minus v and this is minus v. So, it is v square, which is dfn. So, what does that mean? That means this sigma, this discriminant is fixed under every sigma. So, that means this discriminant Fn belongs to the fixed field of Sn of the rational function field in n variables. But we know it by Newton's theorem. We know Newton's theorem. We know that this fixed field is precisely the field, quotient field of, it's a function field in elementary symmetric polynomials S1 to Sn. This is this is a Newton's theorem, this equality. And we have proved that dfn is an element here. So, therefore, dfn is actually we know it's a polynomial. Therefore, dfn is actually belongs to the polynomial ring generated by S1 to Sn over k. This is a polynomial ring we have checked last time. This is a polynomial ring. Because we have checked that S1 to Sn are algebraically independent, and this is therefore discriminant is a polynomial in S1 to Sn. All right. Also, you can check this, I will not use, but it is interesting to mention. This is a polynomial in S1 to Sn, and the multi-degree of this polynomial dfn is 2 times n minus 1 comma 0 0 0 0. This is the degree of the highest monomial which appear in this polynomial. Note that when n is 1, d of fn is 1 if n is equal to 1. Because in this case the matrix is identity matrix, therefore the determinant will be 1. Anyway, so that was, so we have proved that the discriminant is a symmetric polynomial, and therefore it is a polynomial in elementary symmetric functions. Now we can do a general definition. So general definition of the discriminant of a polynomial. And this will actually, we don't need over a field, we can do it over arbitrary commutative ring, but this course I will stick to the field. So start with any polynomial f, fx over any field in one variable, k, any field, and write it as, and I can assume it is monic. So f is monic f monic of degree n. So f looks like x power n plus a1 x power n minus 1 plus an minus 1 x plus an. Any polynomial of degree n monic look like this, where these ai's are the coefficients, they are in the base field k. All right. Then we know what is the relation between ai's and the roots of this polynomial. Now remember, we have to enlarge our field. So let L over k be a finite extension finite field extension of k such that f of x splits into linear factors in Lx. This was what we proved this theorem long back due to Kronecker. That means what? In symbols fx, we can split this into linear factors, because f is monic, all factors are linear. So it is like this, where x1 to xn, they are precisely all zeros of f and they all lie in L. There could be repetition. So v of f is therefore x1 to xn, and they all lie in L. And what is the relation between these xi's and the coefficients that we studied last time? In fact, what we know is, in general, for any r from 1 to n, minus 1 power r times ar, this is nothing but the elementary symmetric function SR, and then evaluate this at these zeros. So S1 is the A1, that is the first coefficient, and so on. First means coefficient of x power n minus 1. So therefore, we know that dfn, this is a polynomial in these guys. Therefore, when I evaluate this symmetric polynomial at these points, that is minus a1 etc., minus 1 power r ar etc., minus 1 power n an, this is actually indeed an element in K. This is also what we proved last time. Therefore, this makes sense, and this is called the discriminant of f. So we say that then df is by definition, take dfn and evaluate this dfn at these points. This is an element in K, because I have evaluated, this was a polynomial in n variable over K, and I evaluated at the points in in K. Therefore, this is indeed an element in K. This is called the discriminant of, of f so let me write in a proposition. So formally what we did the following proposition. Let f(x) in kx be a monic polynomial of degree n and x1 to xn are in L be all zeros of f in a finite field extension L over k, then df is by definition the discriminant of fn evaluated at those things, but that is same as v of x1 to xn square, which is same thing as product 1 less equal to I less than j less equal to n xj minus xi square. This v is a Vandermonde, not the zero set. So slightly one has to be careful while reading the notation b, but I will not, this v will not come so often. So df is this. So moreover, all zeros of f are simple if and only if Tf is non-zero. All. So discriminant is a constant which measures the non-zeroness of the discriminant, measures whether the polynomial all roots are simple or not. So it is visible here. The last statement is very clear from this formula, because if the two roots are repeated, this product will be 0 and therefore df is 0. Conversely, if df is 0, this is in a field k, therefore k and this product is in individually, you think of it as an element in a field L and this product is 0, then at least one component will be 0 and therefore at least one 0 will be repeated. So this is a good measure for the, and what is the proof? So let me write the proof formally. So proof. So what is by definition? D of f. I want to prove df equal to somebody. So d of f is by definition d of fn evaluated at minus a1 etc minus 1 power n an, but dfn is by definition v of x1 to xn, capital X1 to xn whole square and that this is this one was same thing as d of fn evaluated at x1 to xn, and this is same as this evaluated at x1 to xn, but this is same thing as product. This is the definition of this 1 less equal to I less than j less equal to n small xj minus small xi whole square. That's it. That's it. So the proof is very simple. Now some small values you can calculate by hand. So for small values of n, one can compute the discriminant For example, when n equal to 1, d of 1 is by definition 1. What will be d of x plus x1? This is n equal, no, this is n equal to 1 case. N equal to 1. What is the discriminant now? Yes. So, what do we have to do? Degree 1. So, there is the what is v? There is only one root, and therefore it is 1. Okay, what about now degree 2 is interesting, n equal to 2. This is what we did it in the school days, right? I have the quadratic polynomial, it's written like this in our notation, and therefore we know if you would have written, so if you know this polynomial as x1, x2, they are at most exactly two roots. If you count with multiplicities also, it is written like this, and therefore what we get is S1 evaluated at x1, x2, this is a1 minus a1. So, minus of this is a1, but this one is minus of x1 plus x2, and S2 x1 x2 is, this is the product x1 x2, and this is equal to a2, and therefore we want to get rid of this x1 x2 and write in terms of a1 a2. So, the famous formula is x1 x2 whole square, this is the square of this, which is a1 square, and then how do I get rid of the middle term here, that is minus 4 x1 x2, which is minus 4 a2. This is same thing as x1 minus x2 square, or I have written it is same thing as x2 minus x1 whole square. This is the van der Waals square, and that is this. So, this is our discriminant of f, d of x square plus a1x plus a2. So, this is the discriminant. So, remember in a school notation, I will just want to remind, in the school notation we were writing like this, x square plus bx plus c, and the discriminant was square of this, that is b square minus 4c. This was our school notation. But I want to adopt this because we want to go on higher degrees. All right. So, we have for cubic already we will have trouble to calculate. So, our strategy will be to learn more so that we can compute. Okay. So, now the question is the following. So, therefore, we know definitely the discriminant of a polynomial which is in the constant, which is in k, and this one is v square, where v is the van der mode of the zeros of f. So, this is van der mode of the zeros of f, and this v is not in k, this is in L. This v belongs to L and it may not be in k. So, v is in L, where L is splitting field of f. It is enough that we adjoin all the roots of f to that k, x1 to xn. Therefore, this df is a square in L. So, clearly df is a square in f, square in L, but it may not be square in k. See, it is an element in k, but in the bigger field it is a square, but we do not know whether it is in a smaller field it is V square or not. That is very important. Now let me state one theorem. So this is very important theorem. This is due to Cauchy, proved in 1815. This says that if I take the function field in n variables, I know the group Sn is operating on this. I know the fixed point, that was the Newton theorem, but now I take the subgroup here An. This is a subgroup. So An operates on this, on k x1 to xn, and I want to consider the fixed field. So the fix An of the rational function field, what field do I get? So this, obviously it will contain this field k s1 to Sn, is contained, because these guys are fixed under all permutations, in particular this one. So this fixed field is smaller than this, but this equality I want to write, this is nothing but adjoining the square root of dfn. This is what I want to check. That is the Cauchy's theorem. So the fixed field of the alternating group is precisely generated by a square root of the discriminant of a general polynomial over the rational function field in elementary symmetric polynomials S1 to Sn. That is the theorem. Proof is very simple. We will finish it off. So proof. Okay. What did we check? So what is, first of all, dfn? Square root. The square root is v. This is van der Mode. Because dfn is v square, so the square root is v. And what did we check in the lemma? We have checked that sigma applied on v is nothing but sine of sigma v. Therefore, if if sigma is in n, then this is nothing but minus v. So definitely this v is not fixed under this. Therefore, the fixed field, so let us call that fixed field of n of the rational function field, this fixed field definitely contained in the rational function field, and definitely it contains k s1 to Sn. So I want to call it M. Let us call this as M. This is an intermediary field between this, and we have checked that this extension is a Galois extension. Galois extension with Galois group Sn. This we know already, and this is a fixed field in between. So, and what is therefore the fundamental theorem of Galois theory? What does it say? It says that the fixed fields will correspond to the group, right? So so this M will correspond to this intermediary field. This will correspond to the Galois group of L over M. So L is this big field. So this is under the Galois, this is the fixed field of, this is fixed in L. So L is the rational function field. And now K was not the K, but this considering over K S1 to Sn. This is Galois. So this Galois group corresponds to this fixed field, and we want to compute this one. But what is this? This this you get back n, right. That is precisely the fundamental theorem of Galois theory. And this index will correspond to the dimension, that is m over k, m over this k S1 to Sn. This was precisely information from fundamental theorem of Galois theory, but this index we know it is 2. So, therefore, this degree is 2. That means m is generated. So, but this is obvious, k of S1 to Sn, this m is here and m definitely contains k S1 to Sn adjoined with V. This is definitely contained here, because V is also in M, because V is fixed under all elements in the alternating group. So, therefore, this is clear, and this degree is 2, that we know it because this index is 2. Therefore, we have no choice but equality here, and once it is equality here, that is what the assertion was. So, this proves m equal to k S1 to Sn adjoined with V, but this is same thing as k S1 to Sn adjoined with the square root of a discriminant, but this m is nothing but the fixed field of n of k rational function field. So, that this was precisely Cauchy's theorem. Of course, Cauchy did not prove it this way, because Cauchy did not know what is fundamental theorem of Galois theory. So, this is a modern proof of, you can say this is a modern proof of Cauchy's theorem. Okay. With this, I will stop and we will continue in the next lecture. Thank you.